Okay, on this video I'm going to do at least part A of this problem, maybe parts A and B depending on how long it takes. It says to prove each statement directly from the definitions, and part A says that if A and B and C are subsets of U, then A being a subset of B and A being a subset of C implies that A is a subset of B intersect C. Basically, being a subset of both means it's got to be a subset of the intersection. That is true. And the definitions we're going to use, I'll write them up here, is that A is a subset of B when, for all x in A, let me write it as an if-then statement. Let me write it as an if-then statement. X being in A implies that X is in B. Okay? And the intersection of two sets, A intersect B, is defined as the set of all x's such that X is in A and X is in B. Okay? So we're going to use those two definitions here. And we're going to rewrite statement A as that A is a subset of B and B is A is a subset of B and A is a subset of C implies that A is a subset of B intersection C. We're going to write it as an if-then statement. A is a subset of B and A is a subset of C implies that A is a subset of B intersect C. Okay? And I don't really need to put parentheses over here on the left-hand side or anywhere here because there's no ambiguity. I can't have A being a subset of B and A like that. There's no way to interpret an and symbol between two sets. So I don't really need parentheses here, although I could go ahead and do something like that. Maybe it makes it clearer. In any case, we're going to assume A is a subset of B and A is a subset of C. Then X being in A implies that X is in B, since A is a subset of B. And since A is a subset of C, writing sort of the same thing but in slightly different order here, X being in A implies that X is in C. Okay? And now we want to prove that A is a subset of B intersects C. To show that, we show X being in A implies that X is in B intersects C. Okay? And so what we're going to do is now with the facts we have from this premise, we're going to prove this conclusion. Now this conclusion itself is equivalent to this if-then statement. So now we have a new if-then statement we're proving, and what we're going to do is prove it as sort of a sub-proof, you could think of it as. We're going to let X be an element of A. And we want to show that X is an element of B intersects C. Well, to show that, we must show that X is in both B and in C. And we're going to get that since X is in A, and since X is in A, X is in A implies that X is in B, we have X is in B. Okay, these two together give us that X is in B. Similarly, X is in A and X being in A implies X is in C. So hence X is in C. Then we have X in both B and C now. X is in B and X is in C. Hence X is in B intersects C. And that's what we had to show. And so we're done now. Okay, so that's part A. And straightforward application of these definitions, okay? And you just have to, at each step, keep track of the pieces of evidence. Basically what we do is we take this premise here, break it apart into all its constituent pieces of evidence, and then we're essentially just putting those pieces of evidence together in a slightly different way to show the conclusion. And I'll do part B on another video here.